pieces about a graph: increasing, decreasing, concave up, concave down, local max, local min, and inflection point. And if you notice, when we do this work, we have to identify the first derivative, and we have to identify the second derivative. Turn to the person next to you. What do each of these tell you about each of these? Which one tells you what about which? Go, talk. 5, 4, 3, 2, 1. First derivative is which ones? Increasing, decreasing, local max and local min. Okay, those are our first derivatives. Our second derivatives will be concavity and inflection. Okay, a lot of people that they get to the test, they say, I never understood concavity and inflection. Okay, we're going to try to make sure we understand that better within these couple examples. I have to find my first derivative. How are you going to do that? Quotient rule. Derivative of the top. 1. So I get 1 times x plus 3 minus, what's the derivative of the bottom? 1 times then x minus 1 all over x plus 3 quantity squared. What are you going to get in the top?
2, 4. Wait, no. 4.
4 over x plus 3 quantity squared. Is the top ever equal to 0?
No.
Is the bottom ever equal to 0?
No.
Yeah? For what value?
-3.
-3. So I'm not going to create a graph this time. I'm going to create a number line test. Remember how in the previous lesson I told you how to make a graph and determine all that information? You don't have to make a graph. You could always just do a number line and test points. So I'll show you how that works right now. This should bring you back to your college algebra days with me. Back in chapter 1.7, we did that. I'm going to plug in a number to the left of -3. Addie, what number to the left of -3 would you like to plug in?
-4.
-4 plus 3?
1.
-1 squared?
1.
And 4 divided by 1 is? So that is positive. Hannah, give me a number to the right of -3. 0. 0 plus 3 is 3. Squared is 9. 4 over 9 is positive. You could have looked right away and just understood true or false. The top is always positive.
True.
True or false, the bottom is always positive.
True.
Yeah, so it was going to be positive either way. But I just want to show you how you could do a number line test to indicate as well. What does that tell us about increasing, decreasing? It's always increasing, except at what value? -3 is not part of the domain, is it? So it may not be included in our intervals of increasing, decreasing. It's increasing from -infinity to -3, union -3 to infinity. It is decreasing never.
Hold on. What was it increasing?
-3.
-3, then -3 to infinity.
And then you can't go cut it. Okay, never mind.
Can't count -3 because -3 is not part of the domain.
Sure.
Everybody agree we have a vertical asymptote that occurs at -3? Okay. A local max happens when the first derivative changes from positive to negative, right? Positive to negative. Does this ever change from positive to negative? No. So there is no local max. Local min happens where it changes from negative to positive. Does that ever happen? No. So there is no local max or no local min. All right, we learned what we can learn from our first derivative. Let's do our second derivative. Pair it with the person next to you for 15 seconds. Talk about what derivative rule would you use to find this derivative. Talk, go. 5, 4, 3, 2, 1. I'm using the chain rule. If you want to use the quotient rule, go ahead. It takes a lot more work. I find the chain rule in this situation is going to be quite easy. I have 4u to the -2, and I have x plus 3. The derivative of x plus 3? 1. Derivative of 4u to the -2? -8 over u cubed. And thus we have negative 8 over x plus 3 cubed. I'm going to set up my number line test in this scenario to be able to determine where it's positive and where it's negative. Is the top ever equal to 0?
No.
Nope. Is the bottom?
Yes.
Again at negative 3. I'm going to plug in what Addie said, which was negative 4. Negative 4 plus 3 is negative 1. Negative 1 cubed. Negative. And a negative divided by a negative is a positive. We move over to 0. 0 plus 3 is positive. Cubed is positive. Negative 8 divided by positive is a negative. What does that tell us? You decide what it tells us. Quick Karen share, take a minute.
It says negative infinity over 3.
Yes, it's supposed to do math.
Maybe.
Oh.
Sure is. Sure. Yep, we'll do.
Addie, would you like some?
Lily?
Thank you. In where? Mary? Who's Mary Larson? Never heard of her.
Okay. The second derivative tells us its concavity. It is concave up from negative infinity to negative 3. It is concave down from negative 3 to infinity. The definition of inflection is where the second derivative changes sign. Does the second derivative change sign? Yes. At what value? Is negative 3 part of our domain? No. It is not part of our domain, so it has no inflection point. Yes, I will. So I'd like to explain what this means by looking at the graph. We happen to know very well what this graph looks like. This graph simply is a graph that looks like this. Okay, I'm going to go ahead and make a horizontal asymptote here. Don't worry about how we know some of these pieces. We don't know this yet. It goes through 1 for a horizontal asymptote, and then it goes through negative 3 for a vertical asymptote. Okay, that's what we know about this rational function. It says that it's always increasing. If it's always increasing, is it going to look like the green graph? Or is it going to look like the black graph? Everybody agree that the green graph is always increasing? Whereas the black graph is always decreasing. So we're not the black graph, okay? Now let's talk about concavity, okay? So this, is it concave up or concave down here? That's concave up. Some people would say it's holding water. Whereas if you're like this, that's concave down, okay? It would be emptying out water, however you want to think of it, okay? So this is concave up, that's concave down. So we know it's either those two or it would be the blue ones, okay? So look at the blue ones. This is concave down, concave up. This is concave up, concave down. As you look here, it starts concave up and it ends concave down. So we know it's the green graph and the black graph. It's the green graph and the black graph. Now, that's concavity for a rational function. If I could come back to a little bit different scenario here. Okay. So as people talk about concavity in other calculus classes, some teachers have talked about letting it rain. Okay. And if the part of the graph is collecting water, then it's concave up. If it's shedding water, then it's concave down. So notice in this region here, it's collecting water, isn't it? So that's your concave up. Whereas in the green section here, it's shedding water off to the side. So that's concave down. It's not a very good mathematical explanation, but it tends to give people a little idea. Somewhere in there is your point of inflection where it changes.
And that's only for the second degree.
That's your second derivative, yep. Okay with that? So that's I already knew what the function looked like. And as you can see, there's no point of inflection. It does change at -3, but there's no point we can plot. And as you can see from the graph, there's no local min or local max either, is there? So that's just the graph. So sometimes it doesn't have those characteristics. Sometimes we don't know exactly what the graph looks like, and we venture into it anyway. So let's get to our last example before we kind of do our other piece. You guys are doing well. How are the chocolate chip cookie bars? Do I need to improve on them?
No.
Do you need another taste test tomorrow?
Maybe,
Yes.
yeah.
Okay. I would say there's about a 1 in 1,000 chance that will happen, but we'll see. Okay. When I bake at home for other people, my family gets very jealous. So
Did you not bake any for your family?
I did. They all were able to have one last night, but they were wondering like which pan belonged to them. And I said, well, I'm baking for my flex group because they brought so much money for the food drive,
We
which they
so
did.
I brought $1.50.
And
I
It's-
brought 11.
yeah. And so I was, pretty happy with my flex group for doing it. So I said I bake for them. And so, when I said that, then they said, well, do you have to bring both pans for them? Like, well, I might need more than one pan. It could be close depending on who shows up that day. They said, well, what are you going to do with the rest of it? I said, well, I'm going to give it to my calculus class. And then they say, does the calculus class deserve?
Absolutely.
Do they deserve? And I said, absolutely. And they said, but what have they done to deserve chocolate chip cookie bars? And I said, they've taken calculus. And my wife reminds me that she's taken calculus 2 and organic chemistry. So I have to save some to give to her because she's taking a little bit more math and science than you guys have. So
It is also older than us.
okay, for the sake of the video, Kelly, when you hear that, I'll play it back tonight. Emma said that you are older. I said nothing about your age, Kelly. Emma is using ageism right now to discriminate against you. She says that you're old, which
I
is
didn't say
totally
she was
not
old. I said older than us.
older than you. Well, that's obvious. Anybody
Yeah.
knows? Of course, she's a parent. She's gonna be older than
Exactly,
you.
So she's been able to have more math and science classes than we have.
Oh, she just did the head bob to me as well, Kelly, right now. Okay, a little bit of an eye roll. So I'll see if you want to come in for a math chemistry challenge with her someday. She'll maybe challenge you someday.
I'd fail.
I don't think she knows her derivatives quite like you do. All right, here we go. Do you know what that looks like? I don't either. Do you know what the domain of the cubed root of x
She knows.
is? Yeah.
No, so when we draw it at the end, we're just drawing that picture up there.
So
Or we
I
drawing the
so to be
derivative?
clear, for this part of the assignment, there's only one situation where I'm having you draw the graph. And that was for problem number 3. When we get to the end, of this unit, we're going to be drawing more graphs. But this would be challenging. All I'm going to do is I'm going to identify these points, and then we're going to graph on our calculator and see if it confirms our graph. Okay? So we have the cubed root of x times x minus 8. Kind of interesting to think about, what does that look like? I'm not really sure. But I do know that the cubed root function looks like that. We've talked about that before, right? So maybe it has some type of shape like that. But I don't know much about the concavity or anything else. So let's investigate as Isaac Newton would. Try to say something intelligent about it. I start by taking my first derivative. What rule will we use to find the first derivative?
Product.
Product rule. The derivative of the cubed root of x.
1 over 3x to the something.
2/3. Very good. Times x minus 8 plus the cubed root of x, or always x to the 1/3 since we've gone down that rational exponent path, times the derivative of x minus 8. What is the derivative of x minus 8? 1. And so therefore we just have that, and we're going to set that equal to Okay, so that's equal to y or whatever. Great. Y prime, my first derivative. Notice how I have a fraction here. I'm most interested where the top is equal to 0 and the bottom is equal to 0, because in the end we're trying to find critical points. Remember, a critical point was where the derivative is 0 or does not exist. Those are two things I'm looking for. Then this fraction could already tell the derivative does not exist at what value? At 0. So I'm going to put this over 1. I'm going to create one fraction. Everybody agree that 3x to the 2/3 is the common denominator?
Yep.
So here I have x minus 8 over 3x to the 2/3. And then I'm going to add that to, what do I get if I take and multiply the top by 3x to the 2/3? 3x.
Wait, oh yeah.
And the denominator of that 3x to the 2/3 is equal to y prime. Or in other words, 4x minus 8 over 3x to the 2/3. Are we okay with that? Okay. So I want to find where the top is equal to 0. Where is the top equal to 0? 2. Where is the bottom equal to 0? So those are the 2 points I plot on my number line test. I don't really know what's going to happen, but I know I need to try plugging some pieces in here, okay? So can everybody agree we could start by plugging in -1? If I plug in -1, do you get a negative or positive in the top? A negative. And if I plug in a negative to the bottom, remember to the 2/3, so you square -1, which gives you +1, and then the 3 in the bottom means cubed root. Cubed root of +1 is 1 times 3 is 3. So you have a negative on top, you have a positive on bottom, which is negative. Now we got to move to the next one. What number are you going to plug in now? We plug in 1 to the top, you get a negative. Regularly, we're going to get a positive in the bottom. So that will be negative again. Then suppose we plug in 3. Everybody see we have a positive in the top and a positive in the bottom? So therefore, we have a positive. What does that tell us?
It's increasing from 2 to infinity.
Good, increasing 2 to infinity.
Increasing from -2
Decreasing from negative infinity to 0. Union 0 to 2. We don't really know what's happening until we know the derivative doesn't exist there. It could be a vertical tangent, right? Maybe that's what happens.
0 and 2 are critical points.
0 and 2 are critical points. What else does this tell me? Local max or local min? Which one? Local minimum occurs where it changes from negative to positive. So I have a local minimum that occurs at 2.
Wait. Okay.
Okay, Hannah?
That's right.
It's okay, Hannah.
Thanks.
Do I have a local maximum? Nope, there's none. Okay, we have second derivative. What do you want to do? Do you want it, so I could bring this up and do the product rule, or I could leave it like it is and do the quotient rule? You want to go to the product? Okay, let's go that route. Or what we could do is we could go back to this piece right here before it's simplified and take that derivative. You see what I'm saying? I think that might be our best bet, huh? I don't really like looking at that guy. Anybody else for taking the derivative of that? Sure. Okay, let's use that. So I have 1 over 3. Whoa, stop that. I have 1 over 3 x to the negative 2/3 times x minus 8 plus x to the 1/3. Is that correct? Is that what I had written up above?
Yep.
Okay. So the last derivative will be quite easy, right? So we're just going to start with this derivative right there. And we'll use the product rule as you said. Again, finding which option to take a derivative of, that's up to you. We had really 3 options. I like this option the best. So I take the derivative of this, I drop it in front, I get negative 2 over 9, x to what power? Negative 5/3 times my x minus 8. We're not going to the x to the 1/3 yet. We're still in the product rule, aren't we? Okay. Then I have plus 1 over 3 x to the negative 2/3. And the derivative of x minus 8? 1. Plus, what's the derivative of x to the 1/3? Yeah, isn't that the same as what we came up with there? This actually looks like it's going to work out quite nicely. I'm going to make sure that I look at my negatives here. I'm going to drop them to the denominator and have this look a little prettier than what it currently is. So in the numerator, I'm going to write negative 2 and the x minus 8. In the denominator, I will write 9 and x to the 5/3. Plus, there's 2 of these, right? So instead of 1/3, it will be 2/3. So 2 over 3 x to the 2/3. Common denominator. How are these different? By what factor? What do I need to multiply by?
3x.
Good, 3x. And that cleans it up pretty quickly. Negative 2 times x minus 8 plus 6x over 9x to the 5/3. We're almost there. I'm going to gather terms here. I have a negative 2x and a positive 6x make 4x. And then I have negative 2 times negative 8, positive 16 over 9x to the 5/3. Great. Number line test for my double derivative. What numbers do we put on our number line test? Negative 4 is where the top is equal to 0 and 0. This looks a little crazy. I've not seen the second derivative as a part on the AP exam. I've seen this problem, first derivative, definitely on the AP exam. And then a question tied to the second derivative, but they don't actually ask you to find the second derivative. So that's why I came up with this one. Let's plug in a negative 5. What will you get in the top, positive or negative? Negative. And if you take a negative to the 5th power, it will be negative, and then the cube root of a negative is still a negative. Can everybody see that in the bottom, if you plug in a negative, it's giving you a negative? But if you plug in a positive, it's giving you a positive. So we've got a negative divided by a negative will give us a positive. Now we plug in, say, negative 1. What will you get in the top? Positive divided by a negative will be a negative. And then hopefully everybody sees if we plug in positives after that, we get positives all the way through. Beautiful. So, what does that tell us? Good. Concave down from -4 to 0. Do we have inflection? Does the second derivative change sign? The second derivative changes sign both at -4 and at 0. For the sake of time, I am not going to find the y values, but I'm going to say at -4 and at 0, I have points of inflection. We wrap up today's lesson with your graphing calculator. Grab that graphing calculator. The original function is the cubed root of x. You have two options for typing in cubed root. A lot of people like to go to math and grab the cubed root piece, which is number 4. My preferred mode of option is to do x and to raise it to the parentheses 1/3 power. That's just how I generally do it. But sometimes the buttons on my calculator don't seem to work very well. Don't say operator error. Times x minus 8. Still can't believe Emma called my wife old.
I didn't. I said older than us, which she has to be to have your daughter. Well, all your kids.
Whatever you say. All right, I'm going to zoom 6. I'm going to zoom, and we're going to see this type of shape we get. Oh, wow. So, you guys tell me, at this spot right here, concave up or concave down? This is concave down right here, isn't it? If I would extend further, I'm going to open up my window a little bit more. I'm going to go -20 to +20. Okay, so it looks like what happens is when you get back here to about -4, it switches to concave up then. So it kind of does, I'll exaggerate the shape at some point. It kind of does that kind of thing. So it's concave up, it's concave down, and then it's concave up. That's the thing that it does. It found that hidden piece right there for the concavity. Does it have a local maximum? No. Does it have a local minimum?
Yeah.
Yes, it occurs as we see as an x value of 2, which we were able to pick up. Look at your local minimum. We said at 2. It has no local maximum. Look about increasing and decreasing as we gather information from here. Increasing or decreasing? Increasing or decreasing? Increasing or decreasing? Yeah, it's decreasing all the way here until you get to that minimum spot, which would be at 2, and then we continue increasing after that. As you look at your information, we notice that's increasing at the end, but at the beginning part, it is decreasing the whole time. We found very, 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 very interesting points about that. What we will do tomorrow is we will not do any algebra. We will simply just do a graphical analysis, followed by a few investigative questions of the AP exam. These normally go very, very well for people. Super, super important piece. So that said, you have about 8 minutes. If you've got a question for me to roll through, I'd be happy to help you out. Pam.
Can you